So actually let us use this idea to actually solve a second order linear equation. So suppose it's given by this factored form, d2xi and d minus 2xi, y equals x here. And we have the simple initial condition y is 0 and y prime 0 equals 0. So this part is equivalent to this form of differential equation. If you expand it, you have y prime part 0, but y part will turn out negative 2 minus 4x squared, so I factor down in this form, it equals x. So that's the differential equation. So the first idea there is that if you look at this differential equation and then you turn it into this factored form and substitute this inside function with z, so that's what we are doing. Z is d minus 2xy, that's y prime minus 2xy. So with that called z, well, so before we move on, this is going to be a first order equation in z, and we need initial condition for that too, to apply integrating factor and definite integrals. So here things are about at 0, so we're plugging in x equals 0 there. So if this is z, y prime of 0 here is 0, y of 0 is 0, therefore initial value of z here in this case is 0. So with that initial value, the differential equation for z is this thing is z, now is this first order equation, which is written like this, z prime 2xz on the right hand side x with initial condition there. So this is first order, and integrating factor here is antiderivative of 2x, which is x squared, that goes to the exponential part. So that's integrating factor. I'm multiplying everywhere. Then this left hand side will be, the antiderivative left hand side will be the product. So I move it up a little bit. So let's integrate this part. Okay, this will be the antiderivative of e to the x squared times z. And since we're doing definite integral, we will have this one evaluated at 0. So if you plug in 0 here, x equals 0, and z of 0 here is 0. So this part is just going to be 0. So left hand side, after you apply the definite integral here and there, we only have e to the x squared times z. And the right hand side, of course, the antiderivative definite integral of this one here. Because of this t factor out there, it happened that it has a nice antiderivative, which is half times e to the x squared. So if you evaluate it as 0, this antiderivative part here evaluated at 1, so that's why we have this 1 there. So I solve this thing for z, so z is isolated, and I have to multiply e to the negative x squared, so that's why it's multiplied to the right hand side. So z is now this function, half times 1 minus e to the negative x squared. Now here we're going back to z and y. The relationship between z and y was the following. Let me show you. Was this one right here. When we make a first substitution, the inside part was d minus 2xi in there, and y. So z is y prime minus 2xy. Alright, that's what this is about. Y prime minus 2xy is the function z here. That's what we have figured out. So once you make this substitution back, it becomes a first order linear equation in y again. So the same method applies. So I move it up here, and I'm multiplying integrating factor. This time is negative 2x, so it's going to be e to the negative x squared, multiplied left hand side. Right hand side, we have e to the negative x squared. This time it becomes e to the negative 2x squared. Now antiderivative of left hand side is e to the negative x squared y, evaluate at 0. So this part will be 1 when you plug in x equals 0, but y of 0, remember that it's a part of the original initial condition that was 0. So that's 0 here. And antiderivative of this one is no longer exact, so we'll just leave it this form. This is specific enough, although it's not elementary. So if you solve for y, that'll be the final answer. So if you do that, you multiply e to the x squared both sides. So here is that integral part multiplied by e to the x squared. So this function, if you go through that operator, which which I'm showing it here, and if you differentiate it 2 times, multiply by this number, and they're supposed to cancel and give you x back. So that was solution. So I'm showing you the solution, and once again, this is the one and only one solution to that differential equation. Thanks.